Good afternoon. We are going to talk about some deep learning concept. And this chapter, we will begin some classical machine learning problems. Okay, so, and then we will move to the deep learning part. Because deep learning is an advanced method to deal with the machine learning problem. Okay, so basically, there are several categories for machine learning, and from their names we can find that they can be applied for different problems. So supervised learning means all of our data has a label, and we want to learn a model or a function so that we can predict the label from our input data. And unsupervised learning means we have no data. Okay, we have no labels. All we have are the data. So for this type of problem, we usually want to cluster them or categorize those data into different groups. And semi-supervised learning means we only partial of our data has the labels, and we want to use those available labels to train a model or to train a function so that we can predict the remaining unlabeled data. And reinforcement learning means this is not a prediction approach. This is we want to train a model. The model can learn a sequence of actions so that it can get the maximum reward. For example, when we play video games, okay, we are the model. We try to learn some actions. For example, I assume most of you know the Super Mario Brothers. Okay, and we need to learn when we should jump, when we should walk, when should we run. Okay, so that we can get the maximum reward. It usually means the highest score or most of the golden coins, or just pass the game. Okay. And for the different categories, their applications are, I should say, some of them have a lot of applications. So this is the speaker in the screen is Andrew Yin. He is a professor at Stanford University, and he came to Taiwan to give a talk last year or 2 years ago. Okay, so this screen is cropped from his lecture video. It is available at YouTube, and he speaks English, so you can watch the video. And okay, from his slide, you can see the green part is supervised learning. It is mostly widely used for current AI applications. And the blue part is unsupervised learning, and the purple circle means the reinforcement learning. So for us, okay, supervised learning is the most widely used machine learning category. So okay, you may have a question. What is the orange circle? It is the generative AI. Okay. It doesn't belong to other three categories. All right. So the difference between traditional or classical machine learning and from deep learnings. Okay, I should use this. Okay, this is a major difference. It means when we, okay, I should say 12 12 years ago, okay, most people use the classical machine learning pipeline. It means the feature they used for machine learning is handcraft. It means our human beings, we design the feature and we extract the feature from, say, images or videos. Then we apply some machine learning method to do, for example, regression or classification task. And the deep learning means this part, the feature extraction, will designed by the network or the machine itself. So we just create an end-to-end. End-to-end means from input to output. The input usually are some videos or images for computer vision, and the output usually means a loss function or loss value. We want to reduce or minimize the output value from those input, and when we adjust those weights, we also adjust the features extracted from the input video or images. Okay, so let's go to what is supervised learning. So for supervised learning, it means we have many training input, and all of them have their labels. Okay, and here we try to learn a model. Okay, the model will build a connection between the training inputs and the training labels. And then once a new input is given, means a test image or test video or test data, then our trained model, it will use it learned parameters, okay, to predict the output label. Okay, so let's see an example. So this is the famous ImageNet dataset. Okay, so you can see there are a lot of images here, and okay, let's see. Okay, so the number of images contained in the dataset is 14.1 million, so it's quite large. And for each class, there are at least 500 to 1,000 clear high-resolution image. And how many classes do we have? It has 80K. So you can see it is quite a huge data set. Okay, so what is the label? The label is the class, the name of the class. So okay. And so let's see what can we see from. So of course this is baseball, and what can we see? It may be a shoe or okay, laptop or monitor. I'm not sure. Airplane. Okay, so some of them are easy to recognize. Okay, and okay, so okay, let's say something extra. So why is there a ImageNet dataset? In the beginning, there is a text dataset, means WordNet. So it means the image here, you replace it by word. So it is an artificial intelligence problem. It means given a word, what is the connection from this word to other words? Okay, so then Fei Li, she was a professor at Princeton University. Okay, she got the idea. She is a researcher for computer vision for many years. She believed there should be a very, very tremendous, huge data set so that many other researchers can use the data set to test their algorithms. So she and her students create the ImageNet data set. Okay, So first, how to collect so many images from internet? Of course, because the dataset was compiled during 2008 to 2010. During that years, there are many images uploaded to the internet, so she can easily download those images. But the second problem would be, how do you label those images? Say, if you have 14 million images, how would you label them? So, okay, that's the real problem she and her students encountered. Okay, in the beginning, they try to label them by themselves, but too difficult. There are too many images to do it. Okay, so at last year, there is a tool called Emerald Mechanical Turk. It means you can just assign some jobs and announce it on Emerald is the American e-commercial company, and there is a platform so that they can assign a job to the platform. Everybody who is an Emerald user who is interested in do the job, okay, can earn a little money. Okay, so it means if you have sufficient budget, or you say if they have sufficient budget, they can hire a tremendous workers for them to label those images. Okay, that's the solution for that. So they talked with some rich companies, and those rich companies would like to agree to sponsor that. So they got a lot of budget and hire a lot of Turkers. Okay, so and yes, so they hire a group of Turkers to label image, and they hire another group of Turkers to verify whether those labels are correct or not. So they created such a huge data set. Okay. But however, in the beginning, they start from the WordNet, because the WordNet provides a template for many different classes, because they have the name of the class. Okay, so from here, once they had such a huge data set, they host a challenge. It means ImageNet large-scale visual recognition challenge. Okay, so from here, from their 80K classes, they only choose 1K classes as the labels of the challenge, and they provide 1200K images as a training set and 500K images as a validation set. They reserve the test image. So they show those test training and the validation set for all teams, and they can build their own algorithm, and they will use their test set to check which one can generate the best clarification performance. Okay, so so that is the concept of supervised learning, and we saw this slide last week. Okay, so this is also an example of supervised learning. So here, okay, let's recall what the algorithm want to do. It means, given a grayscale image, the algorithm want to generate the color channel from the grayscale image. So this is a automatic colorization algorithm. Okay. And so here, what is the input? The input is a grayscale patch, 255 by 255. And what is its target? The target is the values on the AB channel of the LAB color space. Okay, so this is a super. This means the author uses 1.3 training images. So here, this is the learning pair. Their training input, grayscale image. Their training output or label, the AB channel. Okay, so after watching the 1.3 million training images, so they learn a mapping function from the training input to the training output. Okay, so here, given a patch, okay, the algorithm can predict the value of the AB channel, then combine the AB channel back to the grayscale image. It has the 3 components in the LAB space, so it can convert it back to the RGB color space and generate the result like this. So this is another example of supervised learning. All right, so let's go back to the topic of the ImageNet large-scale challenge. Okay, so let's see their performance. So here, in the year of 2010 and 2011, they used the shallow algorithm. So what is a shallow algorithm? It is this, the second row. The feature are handcrafted. Okay, and they apply some machine learning algorithm to predict those labels in the ImageNet data set. And here, in the year of 2012, okay, you see it is 8 layers. It means, I should say, the algorithm of the 8 layer, it has a net. It's named ImageNet. Because the first author of this, I should say, they published a paper. And the first author of the paper is Alexandra. So everybody calls it ImageNet. And the advisor of Alexandra is Hinton. Do you still remember Hinton? Okay. I didn't bring it. I didn't show it a slide here. Okay. Fine. So what you can see from so the vertical axis means the error rate. The lower the error, the better the performance. And from the year 2011 to 2012, the error rate hugely reduced. So, and this is the number of layers used in the neural network. So LXNet only has 8 layers, but the result is very, very great. And from LXNet, neural networks, again, attracts a lot of researchers' attention. Okay, and then 1 year later, this is another version of LXNet. It means it is when it adjusts the number of channels, the width, and the height of the LXNet, and it found, okay, after tuning those hyperparameters, they can get better performance. So from 16.4, the error rate reduced to 11.7. Okay, and here, in 2014, another neural network architecture called the VGG. VGG is the visual geometry. So I forgot the middle of the G. Okay, so it is a deeper network. From the number of layers increased from 8 layers to 19 layers. Okay, and in the same year, Google proposed another neural network architecture called GoogleNet. Okay, it also used around 20 layers. Okay, and 1 more year, the Kai-Ming he proposed a ResNet architecture. Okay, so how many layers the ResNet used in his paper? At most 152 layers. So the number of layers hugely increased. Okay. And why he can use so many layers? Because there is a problem in neural network. It causes the diminish of gradients. If we want to update the weights in the network, we need gradients. But if there are more layers in the gradient will be more difficult to pass from the end to the front. So the advantage of Kai-Ming-Her's ResNet is compute the residence layer by layer rather than the values layer by layer, so that the gradients can be passed from the end to the front. Okay, so who is the Kai-Ming-Her? So let me recall. So we saw this slide last week, right? So this author of this guided image filtering, the first author of this paper is Kai-Ming-Her, and this paper was published in 2006, and 9 years later he proposed his ResNet. So until now, ResNet is still very popular. This is many researchers are still using it. Okay, so here we only see the result until 2017. Okay, so let me show you another interesting thing is, how about a human? If you ask a human subject to do the same thing as a machine, so what is the performance of a human? Okay, so this is the performance of human for the ImageNet data set. Okay, the error rate is around 5.1%. So compare with machine, okay, so from Kai-Ming-Her's ResNet, machines do the better job than human for this task. All right, so okay, so this is the performance for the ResNet dataset in recent years. So in 2000, so you can see ResNet here. Okay, so this is another metric. It means top one accuracy. So top one accuracy means given an image, and the network will predict which class will have the highest probability of this class. Okay, and you can only choose one. So there's another metric called top 5 accuracy. It means you can have 5 choices. If either of the 5 match the ground truth label, it will count this prediction is correct. But this is more difficulty because you can only count the best one. So here is the ResNet 155. You can see year by year or month by month, many other teams, they try to propose better algorithms or existing algorithms. So the blue circles means the state-of-the-art method, and you see many graded circles here. It means some method they proposed, but they didn't outperform existing methods. So now the top 1 accuracy is around 92%. Okay, quite amazing. Okay, all right. So okay, so in the once we build a model or function, what we want is to minimize. Okay, so here, let me explain the symbol. So suppose the xi is the input data. We have many input instances, and the y is the label. Okay, so what we want to learn is the model's parameter w. Okay, so here we tune the parameter. For different parameters, we will have different functions. All right. Okay, and here the function f. We want to predict from our input data to the output label, and we will usually create a loss function. It means here from this equation, it is the average for every instances, because you see there's no difference for this instance or that instance. But however, in the real world case, there are other cases. Sometimes the losses are uneven. For example, if this is a medical case, a patient went to goes to a hospital and do a check whether he has a cancer or not. Okay, so if the predicted result is no, you don't have the cancer, but in fact the patient has a cancer, then and according to the false negative prediction, okay, the cancer may grow up, and sometimes will create a huge damage. Then the loss will be very large. Okay. On the contrary, if the prediction tells the patient, yes, you have a cancer, but in fact the patient has no cancer, then the loss is very minimal. Okay, so so in the real world, sometimes the sometimes the loss is uneven, but usually for our network training, we assume their losses are the averaged as the loss function. Okay, here we are going to some classical machine learning method. So for classification, I should say the first example given in our textbook is a nearest neighborhood method. Okay, so assume this is a two-dimensional example, and there are some existing training example, and everyone has its own label. So there are three types of classes: triangle, circle, and square. Okay, so the nearest neighbor method means given a test input, we want to label the test input. How to do it? Just find its nearest neighbor. And so the next question is, how many neighbors do you need to find? So the number k is a hyperparameter. Okay. For different k, we will get different results. For example, if k is 1, then in this example, the star will be labeled as the circle. So, but however, if we set k is 9, then it will find its 9 nearest neighbor, and then it will find, okay, there are more squares than triangles and circles, so it will be labeled as the class of square. Okay. But if we increase the number of k, then there will be maybe different result. So let's see this example. Okay, given this set of data, so there are only two types of classes. One is orange, another is blue. Then for different k, 1, 2, 3, 4, 5, 6, 10, 20, and 50. Then given a point in the set, then it will find its nearest neighbor and label the location by its colors. So for different k, we will get different classification results. So it will when we do experiment, if we want to use the k nearest k method, we usually need to tune the hyperparameters. Okay, and try to figure out which k will generate the best result. Okay, and okay, so here, this is another classification approach named Bayesian classification because it uses the probability model. Okay, suppose we can get the analytical model of the function, then it means we have several classes, and we can know the value of the probability, okay, given a class and its input data. We know its probability, and we even know the prior probability of a class. Then, okay, we will predict the probability of the input data under certain I should say, given the input data, we will predict the probability of each class as this equation. It means, okay, here this is prior probability times its conditional probability. So, and this is the summation of every type's probability. All right. Okay. So this equation has a name. It's called a softmax or normalized exponential. Okay. And here the LK, okay, it's just since okay we convert this equation to the exponential ki. So what is ki? Ki is the potential of this equation. They are totally equivalent. But however, why we need to emphasize here? Because the LK here has a name. It is the likelihood of the class K. And usually we will use this equation. Softmax means the overall expression. Okay, so let's see an example. So we can see these figures in our textbook. Suppose we have only two classes, and the probability distribution, and we only have a one-dimensional input value. This is the x. So suppose this is the probability distribution for the first class, and this is the probability distribution for the second class. Then the posterior probability for the first class will be this, and the posterior probability distribution for the second class will be this, and we will set a decision criteria. It is the green line here. Okay, if we see the x value is less than the decision boundary, then we will predict it is the class 1, and if it's greater than the decision boundary, we will predict it as the class 2, so that we can minimize the misclassification rate. It means for if we observe a value of 0.4, okay, it doesn't mean it always be the class 1, because the probability to see the input value as 0.4, but it is from the class 2. The probability is not 0. Although it is very, very low, So what we want to minimize is the overall misclassification rate. It is something like this. Here, what we want to minimize is the overall loss. And in that example, it is the overall misclassification rate. Okay, so it depends on how do we define the loss function. Okay, so there are very widely used function called logistic function in classification problems. So the mathematical definition for the logistic function is this. So 1 over 1 plus exponential negative L. Okay, so it usually will use the symbol sigma to express it. So what is the logistic function? So if we want to see a figure, the red curve is the logistic function. Okay, so what does this mean? It means no matter if you have a very small or negative L value, your return of the logistic function will be 0. And if you have a very large L value, the logistic function will be 1. So what does this mean? It is mapping from a real number to a probability number. So, so if you can find two values, one is greater than another, you will say, okay, if I want to create a mapping function from the two values to a probability, you will say the greater value should be predicted to a higher probability value, and the smaller one should be predicted to a smaller probability value. So if you have any function, it is the S-curve from 0 or a certain number to another converged number. That will be called sigmoid. Sigmoid means the shape of S. Okay, so let's see another example. This is a probability function. It is the accumulated probability value of normal distribution. So it is also a sigmoid function, but it is not the logistic function. Okay. Because so what is the shape of the probability function? It is the blue dashed curve. Okay, so in our textbook, our authors deliberately show the two functions and adjust the parameter coefficient lambda to draw the probability function so that the slope of the two functions, one is logistic, another is probability, at the center region will be the same. But however, both of them are sigmoid functions, but they are two different sigmoid functions, and only this is called logistic function. Okay, so why do we need to know the logistic function? Because, okay, suppose this is a binary classification case. It means we only have two classes, either C1 or C0, okay? And from the definition of the probability, probability. Okay, it will. So let's see 5.2 again. Okay, so this is definition of the Bayesian classification, and if we expand it, okay, we will get the result. Because we only have two classes, so it will become the L1 and the L0. And if we move the term from the exponential to another, so we'll get this. And because both of them are exponential values, so they can be expressed in this form. Okay, and we get the negative sign out, and so this is what it becomes a logistic function. Okay, so here it means if we have the difference of the two L values, we can know the difference of the probability. Okay, and if for another case, if they are Gaussian distributions and they share the same covariance matrix, then the probability of the two cases classification problem will be expressed in this form. So this is a definition of the Gaussian distribution, and we use equation 5.2, the Bayesian theory. We will get the probability given an input x and its the probability for the class 0. Okay, and we expand this equation, we will get this. It's a very long, complex expression. However, there are some constant terms here. This is constant, and this is also constant. We can remove that together because this is a division equation, so it is slightly clear in this format. Then, similarly, we move the term from its nominant to its denominant. Okay, we will get this, and because they are exponentials, so we can move them into this way. Okay, and finally, if we open the parentheses and sort them out, finally we will get this expression. So here you see this is the logistic function again. What does it mean? It means given an input vector x, we can find a linear mapping function in terms of w. Okay, so w will be expressed in this format. Then we can project the input data or input vector x to a line in the high dimensional space. Okay. And on the line, we will have what? We will have, so you can assume this is the projected line. Then we can use logistic function to convert the value from this line to its probability. Okay. So that's the meaning of the logistic function. And the author of our textbook gives us an example. Say, suppose there are two Gaussian distributions in the two-dimensional space. One is the probability of their are shown in the red and blue, I should say, bear shape. Okay, and the posterior probability of the first class C0 will be shown in this way. So if the coordinate of the x is more closer to the left side of this region, okay, the probability of the first class will be greater. And on the contrary, if the location of the input value is more close to this side, then the probability of its class for the second class C1 will be higher. So of course, the probability for the first class C0 will be lower. So it will look like this shape. And if there are more classes, more than two, Then, okay, the linear regression log likelihood will be extended in this format. So there is another weight vector wk, okay, and but however, we can still predict input vector to a line and use the predict mapping value to predict its probability. But here you see there is assumption. The assumption is the two Gaussian first they are Gaussian distributions and they share the same covariance matrix. Otherwise, those equations don't work. Okay. However, what if there are different, if they don't share the same covariance matrix, what will happen? So this is the case. There are three Gaussian distributions. The first one and the second one share the same covariance matrix, but the third doesn't. Okay, because if they share the same covariance matrix, the shape of those circles will be the same, but however it will become. And however, we can still, I should say, so this is their decision boundary for the first and second. For the green and the red one, it is a straight line to separate the two distributions. For the third Gaussian distribution, okay, the decision boundary will be a quadratic curve. So, so you can see the shape here, and for a Gaussian distribution, it okay if the covariance matrix is the same, we can use a linear mapping function to separate it. But for different covariance matrices, we cannot use the linear projection. But however, we can still use a quadratic equation to project it. So there is I should say, okay, now I should say we assume they are Gaussian distributed, but however, if they are not Gaussian distribution, so what should we do? There is a famous method called Fisher linear discrimination. It means we don't know the distribution of those input vectors. However, we can try to find a mapping, linear mapping from those high dimensional vectors to a line. Okay, so in this example, we project those input value vectors from this to this line, and in this example, we project them onto this line. So what's the difference? Okay. The difference is shown on the histogram of the red and the blue points. Okay. For here, you can see there are still some overlapping regions. But if we project into this line, the overlapping histogram bars become very, very small, or even zero. So it means this projection from high dimensional spaces to a single line will be easier for us to separate the two groups of training points. So this is what Fisher linear discriminant want. He want to find the best projection. It is still a linear projection from the high dimensional input vectors to a single line. Then what it can do? The same. We project the x input through a linear projection to a logistic value. Then we use the logistic function to predict its probability. And in this case, it means the logistic value for this group and this group are mostly separated. So that's the meaning of the visual linear discriminant. Okay, so let's take a break. Okay, so let's go to our textbook. All right, what we are going to talk about is the cross-entropy. It means it is a loss function. So what we want is to minimize the loss function as little as possible. Okay? So let's think a very simple condition scenario. We only have two classes, C0 and C1. Okay, and we have a set of training examples. So this is our X input, and the T means our label. So let's go back to this slide. Here, this is we have X input data, and then we have label. Okay, we want to minimize the loss function, and here the label Y we have has its value. The values are either 0 or 1. Okay, that's the binary label. Okay, and we use the logistic regression to estimate its probability of P1. So the mathematical expression of the probability formula will be this: P1 to the order T1. T1 only can be 0 or 1. And 1 minus P1 to the order 1 minus Ti. So let's check. Okay. If Ti is 0, so then the value of this formula will be, because this is 0, so the 1 minus P to the order of 0 will be 1 minus P1. And this term will become 1. Every values to the order of 0 will become 1. So it will be 1 minus P1 to the order of 1. It is P0. And if the label is 1, then here this term will become 1. So we can ignore it. Then the probability will be P1 to the order of 1 is P1. So check. Okay. The equation is correct. And so this is just for a single instance. And we have a set of training instances. So their joint probability will be the product of all of those probability values. So here's product. And if we take its negative log value as a loss, which will be this. So the product becomes the summation. And the P1 to the order of T1 is here, okay? And the 1 minus P1 to the order 1 minus Ti is here. Okay? And we take its negative value. Why do we need to take its negative value? Because of the log. So this is the curve of a log function. And all probability is greater than, actually in the range of 0 to 1. So it's only this region, 0 to 1. Okay, and all of its log value is greater than 0. And the smaller the probability value, the smaller the larger the negative value. So we take it a negative value as a loss. So if the probability is smaller, the loss or the penalty will be higher. Then we extend the two-class scenario to the multiple classes scenario, and we will have the probability value symbol PIK as this term. Okay, and the ZI is only the normalization term, because all of those probability values should be summed up as 1. And the multi-class cross-entropy loss will write in this format. Here, the PIK means the probability for instance k, and it is and the class for instance p and the class k. Okay, so here you can see something special here. The tilde tik, it is a one hard coding. It means if the xi belongs to the class k, then the value is 1. Otherwise, the value is 0. So, okay, the next question is, now we have the loss function, and we have many training data. How do we find the best parameters? Here is the wk and the bk, so that we can minimize the cross-entropy loss function. Okay, so here it will become a numerical optimization problem. All right, so here, this is another method widely used for the classical machine learning problem. It is very famous. It's called the support vector machine. Okay, so here the idea is we try to find the maximum margin for the two classes. Okay, so this is the margin for that, and we will only care about, so because we want to find the maximum margin, we only care about the boundary points. So the three circles are the boundary points, and all other points will be ignored. And what's the relationship between the support vector machine and our cross-entropy loss? It is here for the binary cases, our class label is either 0 or 1. And here we use another class label. It is the original class label 0 and 1, but here we use the hat t. It means the 2 times of the original label minus 1. So if the original label is 0, here it will become negative 1. And if the original label is 1, here it will still become 1. So now the tilde, the hat t will become 0 and 1. And we have the, so the restriction will become, for this group, all of their linearly projected value, the w times xi plus b, will be greater than 1. And for another group of input points, their projected value will be less than negative 1. Okay, and for the points on the boundary lines, it is called support vectors. That's the reason why this method is called support vector machine, because we are going to find machine in terms of the parameters to separate, I should say, find the maximum margin between those support vectors. And given those mathematical definition, the support machine becomes an optimization problem. It means, given the restriction here, the t hat ti are the class labels negative 1 and 1. This is the restriction. And we want to find the minimum w and b, so that if the w is smaller, then the margin will be larger. Okay. So, okay, here, so the definition of support vector machine is very, okay, I should say this is the fundamental, basic mathematical definition. Okay, it's clear. But there will be another format. Okay, let's recall this. Okay, so in our previous week, we talked about how to interpolate the data in a high-dimensional machine. And here there is a method called kernel regression. The SK means those given data, and we use some kernels or the radial basis function. Okay, we can create the scatter interpolate function, the fx, and the fx here can be used for the supported vector machine. Okay. So if you take this figure, there are red cross and blue crosses here. They are not linearly separable, because if you try to find any straight line here, okay, I should say, okay, let's try. Okay. If you want to find any straight line to separate length, sorry. Okay, there's no way to, oh, sorry. There's no way to do it. Okay. However, if we use the kernel regression function to if we use the kernel regression function to interpolate those input data, okay, so this is the contour of the kernel regression functions, and we apply the kernel regression function to the supported vector machine. Amazing, they become separable. Okay, it means we project those input data to another space, and we separate them in the space. Okay, and when we mapping them back, the straight line. So here, we are going to find a straight line because this is a linear projection. But in the original space, the straight line will become a curve like this. So the two set of group become separable. Okay, for supported vector machine, there's another format. It is the overlapping case. Here we can see this is a restriction. Every point needs to be out of the boundary lines. But in this format, we allow some points in the boundary. Okay, so this is the constraint, and it is replaced by the hinge loss. So what is hinge loss? The shape of the hinge loss looks like this. For the value greater than 1, the loss value is 0. And if the value is between less than 1, it will increase accordingly. So this is the case. When we map the input vector by a linear projection to a line and apply the hinge loss, it will be like this. So for those points, they are they're here. Okay, this figure is original created by Bishop, and our textbook author Selitsky used the figures in our textbook, so the symbols are slightly different. So Selitsky's arrow here is the arrow is Bishop's y. Okay, so it means y is 0 is the separator line, the center, and the boundary is y equals to -1 or y equals to 1. So for those points, okay, the epsilon, this is the definition of the epsilon, is greater than 1. So there is no penalty. But for those 3 points, for these 2 points, the epsilon is less than 1. So according to the hinge loss, there will be some penalty. Okay, so the supported vector machine becomes a trade-off between the hinge loss. Okay, so this is the first term, the hinge loss, and the regularization term. It means the coefficient lambda times the L2 norm of the weight. So here we try to find the minimum regression term, and here it becomes part of the loss function. So here we only I should say support I should say Seletsky, our textbook author, he only used a few sections to introduce the concept of a supported vector machine. But however, supported vector machine itself is a very, I should say, very big research topic. Until now, there are still many researchers use the supported vector machine to solve their classification problem. But however, here you can see, I should say, according to its mathematical definition, supported vector machine can only be used to classify two classes, right? You didn't see the third, fourth, and the fifth classes in the mathematical definition because it looks for the maximum margin between two classes. All right, so if you have multiple classes, how would you do? And this is the reason, I guess, this is the reason Seletsky introduced the decision tree and forest in the textbook. So what is decision tree? So this is the structure of a decision tree. We have a root node, and we have many internal or split node. From our root node, we will go to a split node according to the question or according to the rule used here. And then we will go to another split node. And finally, we will go to the terminal node, or it's called a leaf. So it looks like a tree, but upside down. So this is an example. So given an image, so the first question or the first split rule will be, is top part blue? And yes or true, and it will go to this node. So is the bottom part true and false, it will go to this node. And through this split, it will go to a leaf. The leaf will indicate, okay, this is an outdoor thing. Okay, so for numerical data, so what will happen? It is, suppose in this feature space, there are only two-dimensional, but there are four classes. They are labeled by different colors. Okay, and they have their own probability distribution. Each of them in the space is 0.25%. Okay, the split ones, we are going to find a vertical value because there are two axes. Suppose this is x and y. We are going to find a split of the y value so that it can split the data point into two parts. So the top part will have this probability distribution because there's no red dots here. And the bottom part will have this probability distribution because there's no yellow dot here. Okay, this is only one possible split. If you use different split value, you will get a different distribution. Say, okay. If I split it here, then the top and the bottom distribution will be different. Okay, if I split here, then it will be another different case. So the value of the split, it is a parameter you need to tune, or you need to learn to train. Okay, so there's another way to split it. We split it with this axis. Sorry, I should say. Okay, we split it through this first the x-axis. Again, so suppose this is a high dimensional space. We have many components. First, we need to choose which component we need to split. And the second, what is the split value? So therefore, we have many different choices to construct a tree. Here, okay. So in this case, if we use split 2, then we will get this distribution. So the next question is, what is the best split? Usually, okay, we will choose the low entropy. The lower the entropy, the better the split. So what is entropy? Entropy is a measure of uncertainty. So the lower entropy means the higher certainty. Okay, so this case, if we use the split 1, then this is our result. In the top split, we have possible of 3 classes, and the bottom there are also 3 classes. But if we use the split 2, then the left part will only have 2 possible cases, and the right also have 2 possible cases. So how to measure the entropy? So the mathematical equation is the probability times its log probability and its negative. Here again, you see the negative and the log probability. It's very similar to It's very similar to the cross-entropy loss. You also see the log, the summation. No, the negative sign, the summation, and the log here. Okay, the reason is the same. All probability value can be between 0 and 1. And if you take its log value, all of them will be negative. And the smaller the probability, the greater the negative value. Okay. So, okay, here is also why we use this formula. Okay, so let's calculate the entropy of the split. So according to the definition, let's see the split 1. The split 1, the top part will be negative 0.2, 0.3, and 0.5. Okay, so the entropy will be negative 0.2 times log 0.2, 0.3 times log 0.3. And so the first braces is the top part, and the second braces is the bottom part, and their total entropy is 2.06. And if let's calculate the split 2. The split 2 is the left part has only 2 classes, and both of their probability are 0.5. So this is negative 0.5 times log 0.5 plus negative 5 times log 0.5. And for the second left part, the set, there are only 2 classes. So the entropy is expressed here, and the overall entropy is 0.6. It is smaller than the first one, and it is less uncertainty. It means it's more certainty, more certain. Okay. So if we, I should say, if you want to design a decision tree, you will try to look the split which can generate a lower entropy. Okay, right. So what is the tree? The tree is the sequence of split. So from the beginning, we create those splits. Okay, I should say here the tree may not be optimized. It can be created by any rule or any policy. However, it is a sequence of split. So from the beginning, we have a set of training data. Then for the first layer of split, we will 2 branches, and then we will 4 branches, and more and more and more, and finally we reach a leaf. Okay, so this is a tree, no matter what kind of split we use. And the forest means a group of trees or several trees. Here is the example of 3 trees. Okay. So tree 1, tree 2, and tree 3 give the same input test data. The tree 1 will generate a predictor result. The tree 2 will generate another, and also the tree 3. So what is the forest? If you use a forest to predict the label of input data, it means you go through tree 1 and get a result. Tree 2, another result. Tree 3, the third result. Then average them. Get the average the result of the prediction. It means a forest. Okay. And here, let's see an example. So for a forest, there are some parameters, or I should say hyperparameters. So how many trees should be included in the forest? Okay, this is the first semester. Second, how depth a tree should be. So here you can see the depth of these trees: 1, 2, 3, 4, 5, 6. Okay, and another hyperparameter, when you split a node into 2 nodes, okay, how many samples you should use? Okay, that is the third hyperparameter. It's a law here. Okay, so given this example, this is a very widely used toy example of. However, it's a very famous example. It's a spiral pattern with 4 different classes. Okay, and okay, so here, if you, I should say, so the first is this is a shallow tree. The depth of the tree is only 5, and for this row, there are more depths. The depth is 13. Okay, and here, how to the difference of this columns, these columns, and okay, let me try to enlarge it. All right, so this is axis aligned. It means when you create the split, we can only follow. We will align the axis. It's likely. Let me go back to this slide. Here. Okay. If I split this one, split 1, also split 1 and split 2, all of them align the axis. But if I allow the split can be sloped like this one, then this one, okay, will it create a better split? Maybe. Okay. So that is the result show here. If we allow the split can be a orated line. Okay. So you can see it's somehow like this. Because we allow the split line, it create okay. boundary here. This is the result of the oriented line. Okay, so now let's consider another case. So for the left for the left figure, the low is 500. It will use 500 split, randomly select the 500 points to create a split. But here, it only randomly used 5 points to create a split. So if we use less training point for a split, it is less certain, and the uncertainty will be higher. Okay, so there is a term for random forest. So you create a forest, there are many trees, but however, when you create every trees, there are some uncertainty or random selection of those training points. And let's see, okay, for this toy example, there are only 4 classes. Which one? So there are 8 different settings, okay, according to their depth and law, and whether we can allow them use oriented line. Okay, so from the 8 configurations, which is the best? Which is the best to separate the 4, to classify the 4 classes? So of course it is not this one, okay, and not this one, not this one. So the best maybe this one. Okay, just visually you will see. From here, the red dot, the yellow, green, and the blue. So are they well separated? This one or this one should be the best classifier. All right. Okay. Until now, our author introduced several classification algorithms, and now this is the unsupervised method in the classical machine learning topic. So first is clustering. Here, we no longer have label. We only have data point, and we want to group similar data point into a cluster. And this is the toy. This is really a toy data set. Okay, and you can find the code to create the data set from scikit-learn website. So if you just click the link, then you will go to the website, and then there are some a piece of Python code. Just run it, and you can generate the results. So for every column, it is a method of clustering algorithm. Okay, so the mean shifter, we will show it later, and the spectrum cluster. So let's try to show an example. What is the relationship between those clustering methods to computer vision problems? So this example, given an input image like this, so you can see there are many vivid colors on the, okay? So if you want to do a segmentation, how do you do? So here is an example. First, we convert this image from its RGB space to the L star, U star, V star space. So again, L means the brightness, and the U and the V means the color or chromatic channels. Okay, so it is a 3-dimensional space, L, A, U, V. Okay, and we project this 3-dimensional space into a 2-dimensional space. We remove the V channel, so we will have only the L and U channel values here. Okay, and we apply the mean shift clustering algorithm. on those points, there's no label. We just apply the algorithm, then it will generate a result like this. So the every of the red point is a node. Node means the mass of a cluster. Okay, and according to the node, okay, it means for every point which goes to a node, we will create a group cluster for that. So the result will be like this. For this point, there will be a group, and we use the same color, yellow, to label them. So this is another group, this is another, this is another. So there are 1, 2, 3, 4, 5, 6, 7. 7 clusters for this set of input data. So for the mean shift algorithm, the most interesting part is you don't need to assign any hyperparameter. The algorithm, there is one hyperparameter, but you don't need to specify how many clusters you want. The algorithm will automatically create several clusters. Okay, so let's take a look at this. So say this is the mean shift. So you see, you found the 3 clusters here, 2 clusters here, 3 clusters here, but here you only have 2 classes. Rather than if you apply spectrum cluster, you will have 3 clusters here. So okay, and here again, for the mean shift algorithm, you cannot control how many clusters you will generate. So what is mean shift? So this is a YouTube video. Okay, you can find you can just Google it. Use the name mean shift in spaces, and it is created by the Udacity. And I just cropped it because it will be very easy for you to understand how the mean shift algorithm works. So let's run it. Okay, how to do it?
So we have this region, and we calculate, okay, of all of the points in that circle, where's the mean, or the center of mass? And we say, oh, it's not right in the middle, and that difference between them, that's called the mean shift vector. So this is called the mean shift algorithm. Amazing, huh? And so what do you do with the mean shift vector? Well, you shift the mean, and there it goes, perfect. Okay, what do? We do it again, okay? Here's where we are. Here's the weighted mean of the new samples. There's our mean shift vector. What do? We shift it again. Ta-da! And we do it one more time. There it is. Oh, we're getting close now. Small mean shift vector, shift, and then finally, guess what? We are in the right spot.
So the mean shift means there is a hyperparameter you need to decide. It is the radius of this circle. Once you decide the radius of this circle, from any point, okay, it will, let's take a look. Okay. It will try to group, it will use the circle to collect a group of samples and then compute the center or the mean of the circle. So it will move. So the iteratively move will make every point move to the center of a mass point. So it will generate a result like this. So it means for every point, it will gradually move to the mass center. So from this example, it will automatically generate 3 different clusters. Okay, in the country, there's another cluster method called the k-means. Or means also, it means the mass center. And the k-means, you can specify how many clusters you will generate at the end. Okay, so how do they do? The idea is similar. In the beginning, you need to set k initial locations, and this example the k is 2. Okay, then you just use the distance, Euclidean distance, to label all the input vector data. So here you can see a straight line to separate those input data into 2 groups. So the red group and the blue group, and then you calculate their means. So here, can you see the red cross here? The red cross is the new mean of the red group, and the blue cross is the new means of these blue groups. And then again, use the new means to separate the whole data. Okay, until and repeat it again until it converge. So this is k-mean. Okay, so there's another approach called Gaussian mixture model. This is very similar to k-means, but it uses Gaussian model to so here we use the distance, the Euclidean distance. Okay, this is straightforward. But in a Gaussian mixed model, we replace the Euclidean distance by the Mahalanobis distance. Okay, and we update the means, just compute the average. It's very straightforward. But here we use the EN. EN means expectation maximization. Okay, let's see. Expectation maximization algorithm to again also iteratively update those parameters. So it looks like somehow this. In the beginning, we have initial mixture model, and then we label AV pixels per AV input data's probability. Okay, so what is the advantage of the Gaussian mixture model? It here for k-means, this is a hard split. Every input data, it is either the first group, second group, third group. There is no overlapping. But however, because this is a Gaussian mixed model, every input data can have multiple probability for every classes. So this is one of the advantage. Okay, so all right. Okay, let's take a break. Right. Okay, so let's go back to our slides. Okay, so is there any real world case of the Gaussian mixture model? Yes, here is. Okay, though this is we saw this slide in previous week, and we'll just show it again. For the Yellowstone's old phase geyser, okay, the data set is a mix of two Gaussian models. And okay, so this is the definition of the mixture of Gaussian. So there are several Gaussian distributions, and we use a coefficient pi to sum them up. Okay, and here we mentioned we replace the Euclidean distance by the Mahalanobis distance. And what is the Mahalanobis distance? Okay, the definition of the Mahalanobis distance is this. And where do we see it? It is, in fact, the exponential term of the Gaussian distribution. So what does this mean? So given the Gaussian distribution like this, okay? Suppose, let me enlarge. Okay. For the two star point, which is more closer to the origin. If we calculate Euclidean distance, the top should be more close to the orange. But if we calculate Mohanobis distance, okay, the right one should be more close to the orange. So because there are many circles, ellipse here, it means the same distance from the orange to the boundary. Okay. So the second is the EN algorithm. What is the EN algorithm? There are two steps. First is the E stage. It means we estimate the responses from our formula. So we will get the Z value here. And they look like a probability. So their summation will be 1. Okay. And the second, we use the Z value to update our parameters, including the mu, the means, and the sigma, the covariance, and the pi, the coefficient of it. Those are Gaussian models. Okay, so here, when will we use k-means for computer vision algorithms? Let me show you an example. So this is my paper. I published it 11 years ago. Okay, so this is a supervised single image supervised algorithm. So it means given a low resolution image, we want to create a high resolution image. Okay, so at that time, the existing method, first we would, because the image usually is quite large and we cannot handle it, so we crop a small region. We call it a patch, and the existing method in that year is a single complicated function to generate a high-resolution patch. And for every high-resolution patch, we can reconstruct a high-resolution image. Okay, and my idea is we create multiple simple functions. Given a patch, we pick up one of those functions and create a high-resolution patch to reconstruct the high-resolution image. Okay. So here, first, I need to, how to create this function. Let me introduce this dataset. This is called BSD200. Okay, I use this dataset in my experiment. BSD200, the full name is Berkeley Segmentation Dataset because it is compiled by a Berkeley professor at the university, a professor at Berkeley University. If my memory serves me correctly, the name of the professor is Michael Jordan, but he is not the basketball player. Michael Jordan. Okay, fine. So let me show. So you can see many images here, and for every image, there is a corresponding segmentation label. Okay, and how do they create the segmentation label? Again, human subjects. They invite many volunteers, maybe not volunteers, students or colleagues. For every given image, draw the boundaries of this image. So they will have a set of boundary label, and all of them are different. Then sum them up, take the average, create the ground truth data of those images. And there are several different sets. It means for BSD 100, it means it contains 100 images, 200, 300, and 500. And for every image, the size is 321 times 481. Okay, so this is the first data set I use. But because the data set is widely used at that time, but it is too small. So I mean, the number of images are not sufficient So I use another dataset. It's called label me dataset. There are more than 4,000 images. Why it is called label me? Because in the beginning, okay, it is a web tool to label images. So look at the left figure. Given an image, okay, everybody can upload an image to NIT's website, and there is a web tool for users to label the region, any region of this image. So let's take a look closely. Here is labeled bicycle, and label a window, and label some pedestrians on the street, and there is a car labeled. So the result, okay, so now until now the dataset is still publicly available. If you download it, you will see result like this. There are many different classes and its boundary of the object. Okay. But however, for my research work target, I only use the image rather than those segmentation labels. So let's go back to the super resolution problem. So my goal is to create those simple functions. How to do it? First, let me. So because I have a lot of images, I can create a low resolution images from high resolution images. How to do it? Like this. I just apply a Gaussian filter and subsampling that. So that I can generate a low resolution image like this one from the original one and the low resolution one. Okay, and therefore I can crop patches. For every low resolution patch, I can found its high resolution patch because I want the high frequency signals from the high resolution patch. And so I use a patch 7x7, but I disregard the 4 corner. So the dimension of my low resolution patch is 45. And I want to, so this, for a scaling factor of 4, this is the shape of the high resolution patch. But I only care about the central region, those blue pixels. Okay, then here, this here. Okay, so I collect totally 678 million patches from those datasets. It's a huge number, and I want to apply k-means clustering here. So this is where I use k-means. Why? Because here I want to create several simple mapping function, but I need to decide the number of the mapping function. So this is the k. I use for, okay, but 600 million is too large for my PC. So I randomly choose only 2.2 million patches and run the k-means cluster. When I set k as 496, this is the result. For those patches, these are the low resolution, low resolution patches signal. Okay, so let's see. For this left top corner, this is the cluster containing most patch. And how many is it? The most the largest cluster contains around 18,000 patches. But in the end, for the last 40 clusters, there are only single patches in a cluster. And the mean of those patches are 573. Okay, so this is the natural phenomenon for natural images. For natural images, most patch, the frequency of most patches are very, very low. Only the high frequency patches are very rare in the natural images. Then, once I get those cluster centers, for me it is easy. Just apply a linear regression functions to predict those low resolution features to the high resolution feature. So the low resolution feature dimension of the low resolution feature is 45, and the high dimension of the high resolution data is 144. It means if I have more than 45 training samples, then mathematically it is feasible to find optimized coefficients or parameters to create such a linear regression function. Okay. So since 45 points are sufficient for my target, so I just empirically set 1,000, randomly select 1,000 points to learn the regression function. But so for the cluster containing a lot of training points, it's very easy. So in the beginning, you see every cluster can find 1,000 training example. But for the real cases, you can see it's less and less likely to find a sufficient training point in a cluster. Okay, once I got the coefficient for the 4,096 clusters, I created 4,096, not totally full, because some classes cannot find sufficient training point to learn the regression function. But however, I still have around 4,000 training mapping function. So here, in the test phase, when I have a low resolution image, I crop its patch and its high frequency feature of the patch. Then I map the high frequency feature from the 45 dimensional space to its 144 dimensional space. This is the high resolution space. And then add back the high frequency features to its by cubic interpolated high resolution patch, and then I have a high resolution patch with high frequency signal. All right, so then just sum them up. For the overlapping regions, take the average. I can create the high frequency image. So there are some there is a important hyperparameter, just the k. So for different k, will it generate a different result? Yes, it will. So this is an example. When the k is 512, okay, this is the result. And the k is 124, is twice. Then this is the difference map for the grayscale channel. The maximum value may be 0.4. So if we use the scale from 0, so this is scale from 0 to 1. And usually we will use the scale of 0 to 255, right? So the intensity for the 255 scale times 0.4 is around 10. So visually, it's difficult for us to spot the difference. But if I show the result here, you can see for smooth region, there's almost no difference. But for texture region and edge region, there are some difference. Okay. And so which is better? This one is better. Okay. If we evaluate the result by the PSNR and SSI metrics. Okay, this when the K is larger, the performance is better. And it makes sense since K means how do you split your feature space into K clusters. If your K is larger, then you can have more divided regions, and I can create more mapping functions to get better. If you have sufficient training samples in a divided space, then you can create a better mapping function. But however, the computational load will also increase. So this is the qualitative comparison. Okay, so this is my method. And this is a bicubic interpolated method. From here, you can see the edge is more clear and sharp. And for the textual regions, it is better than bicubic interpolation and better than some existing methods. So the two numbers are PSNR here, 31.6 and SSIN 0.94. The higher, the better. Okay. And this is another widely used benchmark image called Lena. Okay. And here, this is the method created by an existing method. We usually use the first author's name as if they don't have a special name for the algorithm. So this is Sam, Glessner, Wan, and this is ours. Okay, we generated the best performance. But I just cherry picking some good result. Not always, my algorithm doesn't always generate the best result. So if we run, we use 200, the Berkeley segmentation dataset, 200 images for our test dataset. Then we average their PSNR and SSN index. Then ours is almost as good as the Glessner's method. Okay, in SSN we are slightly better than theirs, but for PSNR we are slightly worse than theirs. Okay, but however, the difference of our method and the Glessner method is the computational load, because we split we only need 14 minutes to generate an image, but they need 10 minutes. So, 14 seconds versus 10 minutes. We use much less computational load to generate image, comparable image in terms of their PSNR SSI index. Okay, so this is example how we apply how I use K-means to deal with a computer vision problem. So now you have you see this example, and you may see other examples when you read your own papers. Okay, when I mention K-means, or you can understand, okay, this is a clustering method, and you can assign how many clusters you will get at the end. Okay, and let's go back to another topic. This is the subsection of our textbook called Principal Component Analysis. The concept of principal analysis is a dimensional reduction method. So what is a principal component? It means given a set of training data, okay, if they have certain distribution, and we can find a line, okay, which can mostly present those data, then it will call the first principal component. So in this example, it is this line or this direction. Okay, and then what does it mean? It means for every point, if you project the data onto this line, then then those lines will contain them will be most widely distributed, or it contains the most energy of this type of line. It is very similar to the concept here. Let's go back to the Fisher discrimination, a Fisher linear discriminant. Let's look at it. You have a set of data, and you try to project it to somewhere. So in the Fisher linear discriminant, we try to project the set of data into a line which can separate the two groups of training the data. And in the principal component, we try to find the linear projection which can best present those data from high dimensional to a single dimension. And if we remove the energy, I should say, if we remove the projected vectors of those data, then we will have another best vectors to present those data. It will be the second principal component. Okay. So once one by one, we can find those principal components. So how to compute the principal component? In fact, first you need to find the mean of those group of data like this. The mean will be the center, and then you will calculate the covariance matrix, okay, like the C, and just compute the eigenvector used through the eigenvalue decomposition. So once you get the eigenvector U, they are the principal component. And in the eigenvalue decomposition, you will get the eigenvectors lambda 1, lambda 2, lambda 3. And those lambdas are the lengths of the principal component analysis. Okay. Here, okay, I should say, this is a very, very high level introduction to the principal component analysis. And our textbook author, Risky, he doesn't go into too much detail of this algorithm. You just have the concept, and he focuses on how to use this method or algorithm for computer vision task. So let's see the computer task. So this is a ferret face dataset. It is owned by NIST, and NIST is the National Institute of Standard and Technology. It is a government institute of the United States. Then, what I want to say is, so you see many faces here. Suppose they are well aligned on 3 points, 2 eyes, and the mouth. Then you can create a data set. All faces are well aligned. Okay, when you have a data set, say every face is a point in the distribution, and then you find their principal component. What it will be like? It will be like this. So this is a given image, and this is the first principal component, second, third, fourth, and then they are totally 8. Here only show 8 principal components. And what is its application? So its application is, given an input image, we can use those principal components to reconstruct the image. The C is reconstructed from A. And what's the benefit? The benefit is we can use, because suppose we have only 8 principal component. So we only need 8 coefficients. We can apply the 8 coefficient to reconstruct the image. So here the example is we only need 85 bytes to generate this result. And then what is this? This is the JPEG compressed image. This image used 530 bytes, and which quality is better? I think this is, there are many artifacts on this. So what is principal component? Principal component is a dimensional reduction method. And the dimensional reduction method, so given an image, how many dimensions are there? It means how many pixels are in the image. There are so many dimensions. Say, I don't know, how much is it? Say 40. Suppose this is 40 to 20, then there were 800 dimensions. And then we use 8 principal component in terms of eigenvectors to present the 800 dimensional vector, and we'll reconstruct it. Okay. All right. So now we are going to the deep learning part. So we have seen the classical machine learning part. Okay. So deep learning, we have seen this part already. We show, I should say, statistically list several important machine learning algorithms. Okay, now based on those machine learning algorithms, what we are going to do here is to see how deep learning can extract features from input data. Suppose the input data. So for deep learning, the best concept is the perceptron. Perceptron is a structure. Okay, it means there are some weight and there are some input value. We multiply the weight to input value and multiply the second weight to its second input value and sum them up and plus a BIOS. Then send it to an activation function and we will get an output. So this unit is called a perceptron. Okay. Why it is called perceptron? I should say the structure of perceptron has been invented in more than 50 years. In a very 1940 or 1950, okay. Biology researchers, they figure out this is the fundamental process for our neural cells. There are many neural cells, and each neural cells will amplify the signal and sum them up through another neural cells. And there is another, and reduce or enlarge the neural cells, the input signals, and becomes output signal. Okay. Okay, so the A, B, C figures are the same. They use different illustration, but totally mean the same things. Okay, so in mathematics, the expression become, we have a vector of input value, x is here. So there are many input 1, 2, 3, 4, 5. If we express it as a vector, and there are many weights. The weight is here. How we multiply the weight with the input, and there is a BIOS. So the output, so the S is the linear summation of the input X through weight W and the BIOS B, and there's activation function h. It will use s as an input and return an output s. So here, this is a neural network. It is a combination of several perceptrons, even though it is not organized. Okay. So for researchers, they organize perception into layers. So layer by layer, it will be just easier to compute or easier to model. But basically, they are all perceptions. So we can, if you see this type of illustration from the bottom to the top or from the left to the right, the same. Both figures show the same messages. It means there are some basic input, and then this is on the first layer. There are 3 perceptrons, and then the output of the first layer, the 3 perceptrons, will be the input of the second layer. There are only 2 perceptrons, and then it will be the input for the third layers perceptrons, and we finally will generate the output. Okay, so here, this is a expression for a single perceptron. But if we have multiple perceptrons, how do we express it? It's just like this. We, for every layer, we have many input vector, input value x, so like this. So they are x1, x2, x3, x4, and okay, we will have a matrix W. It will be the weight for each perceptron, and we will generate the vector of output value s. Okay, and so here you will see where is the b in the 5.45 equation. There is a b, but here the b disappears. Why? The reason is b can be merged into the W matrix, because if we extend the tab x into its augmented vector here, it means we added one more constant 1 at the end of the vector. Then it will become this expression. So the output data will be the activation function on the vector of input s. It will be the output of the this layer, and it will also be the input of the next layer. All right. There are many different activation functions. The most widely used is the ReLU. The full name of the ReLU is rectified linear unit. Okay. For positive values, it just return is the original value, no change. And for negative values, all of them will be set to 0. This is most easy to implement and understand. And okay, why neural network is very, very useful? Why can it simulate any kind of functions? Because the non-linearity here. Okay, for positive part, okay, this is linear, but for the negative part, it is non-linear. Already is set to 0. Okay, so you can, but however, there is a drawback of the ReLU function. It means because the return value are all 0 for this section. So when we compute the gradient, here let's mention again, why do we need to compute the gradient? Okay, because this, for us, this is an optimization problem. Okay, if we have a loss function and we need to, for example, this is the multi-class cross-entropy loss. Okay, when we have a loss function, we want to reduce or minimize the loss function based on our trained data, and we try to tune or adjust or update the weight parameter WB, and we need a gradient to try different W and B. So usually when we say gradient descent, it means if we know the gradient of this function, then it is the best way or most efficient way to follow the direction of the gradient and do a line search to find the minimum value of the error function. So we need a gradient. But however, let's go back to the ReLU function. Since this region, the value are all the same, sometimes we will fail to find the gradient because we will get there's no derivative value. Also, the derivative for this section are all 0. Therefore, researchers try different activation function. So, for example, this is Reki ReLU. It reduce the it doesn't set 0 for the negative region, but it change the slope for the negative part and the positive part. Okay, it can avoid, I should say, certainly avoid the problem of 0 gradient. Okay. And here is also a softer plus function. It looks like ReLU, except for the small region, small log negative region. Okay. So okay, here let's go back to the softmax function. We see the softmax function in equation 5.3. It means if we have several classes and we want to predict its probability for those classes, then we use the softmax function. For deep learning or for neural network. So this is a perceptron, and every perceptron will generate a score. Then if it is the last layer of the neural network, then for the A score, B score, and the C score, once we have the score, we will use the softmax layer to generate the probability of the class A, class B, and class C. Okay, so let's take the softmax mathematical expression here again. So it is, so the LK is the A score, B score, C score. The larger the score, the larger the probability value. Why? Because it is an exponential function, and the exponential function is homogeneously increased. So the larger the L or the ABC score, the larger the exponential value. And the denominator is just the sum of those exponential values. Okay, so here show the example. So if the A, B, C, D, E, F are the A, B, C, D, E score, then the probability of ABC will be this. Okay, and then their sum will be 1.0. Okay, another okay, so here you can see deep learning itself is also an optimization problem. Okay, this is a I should say model fitting. When we discovered model fitting 2 weeks ago, okay, you have a model, and then you have some parameters. You need to set the parameters to generate the least loss function or least error, least loss value or least error term. Okay. So you need to have sufficient data to do it. But what will happen if you have a lot of weights to tune, but you don't have sufficient data to train? So it will overfitting will occur. So how to prevent overfitting? For deep learning, there is a widely used approach called data augmentation. If you don't have sufficient data, how to train a model, how to do it, you create data by your own. So this is example. It means this is an MNIST image for the digit 6. And they can apply some method. For example, here they use the elastical distorted method to create the second and the third image. And give them the same label 6, so that once with more training data, they can try to prevent the overfitting problem. Okay, there's another regularization method called dropout. Well, dropout means, so this is a neural network, and there are many perceptrons. And when you train the neural networks, you deliberately randomly set some values as 0. Okay, when you set the output of the value as 0, it means you disable those perceptrons. Yeah. And this method is also proposed by Hinton. Okay, Hinton again. And this method is widely used for many years. Okay, because what the meaning for this approach is, it can prevent the network overly reliant on certain particular unit, because you randomly drop some perceptron out, and so that it cannot use them, it can only use the remaining nodes to learn the weight. Okay, there's another famous batch technique called batch normalization. Okay, this paper was published in ICN 15, so around here until around from 15, so 9 years ago. And you can, I should say, you guess how many citations are for this paper. Usually, citations mean something. If your paper is useful and important, then the citation will be very high. Okay, and for this paper, the citation is more than 350K. So it means there are more than 350K papers cite this paper. This is very, very high. Okay, so batch normalization means, okay, when we train the network, we do not use a single image to train the network. We use multiple images to train the network at the same time, simultaneously. That's the reason why GPU is very important for us. Okay? Because because you see here, all of those calculations are metric. Most of them are matrix computation, except the extraction function. And if you set the extraction function as a ReLU, you still can compute those values parallelly. So here, if we use multiple train instances to train the neural network, we will create a mini batch. Then maybe say 16 images, train the neural network. Why do we need to train? What we want to use those trained data to optimize our weight. We can optimize the weight one by one using a single image, or we can optimize those trained weights by 16 images at the same time. Okay, so the Bayesian normalization means given a batch of say 16 images, then for each we compute the mean of the output value for the 16 images, get a mu, and calculate their variance, and then we normalize the 16 output value. Okay, so so let's see the Inception. Inception is the winner of the ImageNet in the year of 2016. Okay, so this is the original learning curve of ImageNet. If you use more than 30 million images, you will get an accuracy around 0.7. But if you apply Bayesian normalization, you can only use 15 millions and get the same accuracy rate. Okay, so all right. Okay, if you are interested, you can read the paper by yourself. All right. Okay, so that's the lecture today. Okay, do you have any question? No. Okay, so let's keep studying deep learning 2 weeks later. All right. Next week I won't be here. Okay, but I will have a video recording so that I can watch your presentation.